Tibi, I'll call you Tibi if that's okay.
Yep.
So well done. It seems you have combined my understanding of uh, the electro discharge wire machining. That is where they use a deionized water as a dielectric barrier, and more often than not, a 300 micron brass wire to cut up to tungsten carbide. Very specifically,
Yes, it's familiar. The process is familiar, and I was specifically looking into this industrial process and searching for SEM imagery to try to find these typical spheres, but I could not find any. And I was also attempting to look into maybe anomalous heat. At one point, I think I saw something that the dielectric, this deionized water that they use, they need to cool it with significant power. So it seems that maybe it's producing a significant amount of heat, this process, but I have no idea on the power balance. Is it excess
well,
heat? Is
a
it
couple
normal
of
heat?
years ago, I went to a company that's just around the corner from me, and I took some slow motion footage of the process, and I asked for before and after materials. I've shared in my ICCF 25 presentation a couple of the images that I received. I literally only had at the end of a tail end of an SEM session, I had about 90 seconds to look at the active material. And on one side, of course, there's about, I guess, 20% of the material removed, but it's removed in half spherical, sort of partial spherical sections. And so I thought, oh, that's good. And I just slid down this sample, and then there was a sphere of metal, a sphere of carbon with the vortex tail and the carbon on one side. And so for me, the nearly 100-year mystery of how that particular process is now solved, and it is specifically avoiding actual arc discharges. It's using the dielectric barrier, but you have it at a level where it only creates something that isn't an arc discharge and does the job. And I believe it creates this magnetohydrodynamic structure, which includes both hydrogen, oxygen, hydrogen in the form of protons and or atomic hydrogen, and potentially this hidden energy within matter, which all come together to create microball lightning. And it's the boundary layer of the microball lightning that does the has this higher binding energy than ordinary matter, and it causes the matter that it is interacting with to disintegrate in the same way that we've seen in other experiments.
Yes, I think I'm aligned with this hypothesis, and I really prefer it because it would mean okay, uh, end of poverty and solving many problems of the
Well,
world. Of
certainly,
course, if we can
regardless of
manage it.
the excess heat, it gives you known understanding of how very energy efficient processes are generating these phenomena. So, I mean, obviously, this chap here, one Ken Shoulders, he is the man that kind of described this higher binding energy than ordinary matter. But what you've done is you've taken this experiment from Matsumoto's Steps to the Discovery of Electronuclear Collapse, and this is a product of one of these such explosive cold fusion, as he called it. This is a lead sphere with carbon that was formerly inside it, spewing out. But the simple experiment in his case, this is an example of it. He would have a lead wire. He chose lead because he could get it pure. And of course, it's at the end of the periodic table of stable elements. Of course, bismuth is technically unstable. Then he had a copper dish and then a electrolyte in here, typically potassium hydroxide to not have any carbon in it. And the beauty of what you've done is you've gone a step further than this. I mean, his experiments used potentially dangerous 120 volts. But if you look at his page, where is it? Page 240, experiment S70 and S71 here, which I have recommended since my presentation, I think in 2020 or 21 in Azizi, as a simple way to do this. He was doing 4 pulses of 80 milliseconds or 1 pulse of 800 milliseconds.
Yep.
And so because it's AC, it will produce HHO in situ, and yours will do the same because yours is just a pulse discharge, and it can only produce HHO because it's not slow enough. But when the dielectric barrier breakdown occurs, you might have a much higher energy rush going through that, which will do this Shishkin over 5 EV process. And so I think from an experimental point of view, freaking well done. It's a simplification of this. It is a nice way to demonstrate what potentially is going on in the dielectric barrier discharges of electrode discharge wire machining, cutting. And it also achieves the same outcome to a degree as the Ultra experiment. Now, one proviso I have with that, and this isn't necessarily a bad thing. I've done some Ultra experiments where I've used deionized water, the same kind that you have, for about 90 seconds. And in the short period of time that it occurs, you can start to see it getting these collections of iron particles and twisting them up. Now, where are the iron particles coming from? You didn't have a chance to look with SEM, but if you use standard basic kitchen aluminium foil, you'll see that there are incredibly small flecks of iron typically in there. Now you think, oh, well, that's not transmutation. Here's the thing. In the case of what you're doing a very short duration. And that is sufficient, just as it is in the pulsed short duration in wire discharge machining, to create this electrodynamic structure, which in my view is incredibly strong magnetic fields. And the incredibly strong magnetic fields are highly localized, and they yank in any paramagnetic and paramagnetic and ferromagnetic material. And so the fact that it's producing iron-rich crenellated spheres and it may not be necessarily synthesizing that doesn't matter, because you're seeing a process that's able to have such intense magnetic fields that it can create coherent iron in fractions of a second. And that is interesting in its own right. Now, in the resonance system of ultrasound or cavitation systems like Binger and Huang's, these are producing the energy localization and coherence at very small locations continuously, so that the energy can grow and grow and grow, and the condensation of matter and the nuclear processes can go on and on and on. But I think what you've done is potentially simplified, like I say, this and a couple of other things, and got an experiment that is an easy path to creating these iron-rich crenellated spheres. Now, if they are this FeO2 oxidation state, I have argued that they are electron scavengers, and I believe that they can participate in photoelectric dissociation of water. And in fact, as I understand it, the US Department of Energy has been looking for using this particular form of iron oxide to do precisely that. And so I have suggested in past videos that if we could make these en masse, it might be a way to use normal sunlight to create dissociated water, in which case you get an energy technology directly from it. And so in its own right, it could have an engineering
well,
application.
hold that thought. I have a remark here. the exact reason I ended up with this sort of setup with two plain electrodes and distilled water between them and giving it a high DIDT pulse was because of I read about Stanley Meyer's work, this dissociation of water using a process which could not be electrolysis.
Yeah, so
And
I've argued that that process is because of the torsion beam that comes out of the magnetohydrodynamic structure, the toroidal, the opposite end of the toroidal moment. It has a disruption beam. And I believe what's going on with that is it's pulling in, and this is just a working hypothesis, so much dark matter or chi and or something in a vortex, so much so that it over energizes both nuclei and molecules. And one, the very weak polar bonds between normal water at standard temperature and pressure just separate. It becomes water gas. And actually, this is found in, for instance, various types of HHO, that there is actually water in a gas state, but it's not at over 100 degrees. And the second thing is that I believe it's actually separating the water into OH minus and basically radicals. It's basically disassociating the water, but it's not disassociating it thermally. It's disassociating it by disrupting the electron's ability to maintain the OH bond.
the covalent bond, yes.
Yeah, it's not it's not a thermal shaking them apart. It's changing the behavior of the electrons. They actually shift to a different orbit, and this is explained by the work of Xu Wenju. So I did a presentation on his team's work from 1988 to 1999. And it is called if gravity can do this, what is gravity? But he looked at three body alignments, and you might have seen this presentation. Stop me if you have. But just for those that might listen to this at another time, essentially what he was doing was he was looking at four different properties of materials, or these are the ones that he reported in 1999. And that was the spectral output from excited atoms, a sideways movement in a brass sheet, a linear crystal formation during a lead tin alloy crystallization, and changes in atomic clocks. That's rubidium 87 and cesium 137 beta isotope clocks. So we know that because of the beta process, this is a neutrino-like material. Okay, it's for some reason it's changing the decay rate, and since that needs neutrinos, it must be something like that. Although he never discusses that. The second thing is like this Foucault pendulum that was discovered in the 1950s. He had this brass sheet with a weight, and this shows that it actually has an impact on matter, this flux. The third part is the crystallization. It then allows matter to align preferentially, depending on, or it might have been a diffraction of the material, of whatever's in the ether. But the most important one is the change of spectral output from elements. That should not change. And the only way that can really change is if the electron has a different steady state orbit. Okay. And then when it's excited, it goes to a different steady state orbit. So the orbit arrangement of the matter is disrupted. And this is exactly what was claimed by Leonid Aristiev. It was the reason for the absurdly different spectral output above Chernobyl when it had the Chernobyl accident. It wasn't to do with Cherenkov radiation or normal ionization. There was something bound to the oxygen in the air that meant when it did get excited by ionizing radiation, the promotion and demotion of electrons into various orbitals producing photons released photons that shouldn't exist. And so you have a natural phenomena of three-body alignment, and you also have this man-made disaster causing a change in spectral, and this is what I'm arguing. The magnetohydrodynamics, the torsion beam, the disruption beam, which is why we get all these weird things going on, like matter falling apart and plasterboard falling apart in tornadoes, even after them, they're floating through midair and the plasterboard is continually disintegrating. And I'm arguing it's doing that because the atoms and the chemicals in there got oversaturated and the bonds are breaking up. And it's not being hit by anything, it's disintegrating in midair.
Is this a similar effect when you showed a reactor wall made of iron, which was glowing red, but actually
yes, that's it. That's exactly it. That is exactly it.
Radiation.
That is exactly. I say in several videos, I say I call it chi, and effectively it is. It keeps everything running, but in an ordinary sense, in ordinary vacuum state, an atom maintains its electrons by pulling in just what it needs and expelling what it doesn't need. And in the case of being under the influence of one of these clusters, it pulls in too much when it's within a certain zone in this disruption area. In the case of that one, we literally have the video from the inside of the reactor and the video from the outside of the reactor. And in the inside of the reactor, if you look through the shell of the ball lightning by changing the exposure of the camera, you see the tornado going in, and that tornado goes down the tube and touches down on the inside of the tube. What you haven't
I've seen it.
Yeah, what you haven't seen though is that Henk put several different things in that tube. And for instance, a brass screw, and we know brass gets heavily affected by this, and we've seen exactly how in the what I call the cardioid infarction, where it has this hexagonal array and this disruption zone at the bottom of the area of torsion. This brass screw is still roughly in the shape of a brass screw, although it's in a couple of fragments, but it's basically turned to Swiss cheese. The thing didn't melt, it disintegrated in sort of resonant areas.
Yes, similar with the Vega pillow.
Yes, it's all the same thing. So I think what was occurring is it's not an over unity in the sense of there is the energy being put in the system, but there's a net gain in energy because you are causing water to disintegrate into its constituents that then can be later chemically burned. But in you're not actually having to put in the electrical or thermal energy or catalytic thermal energy. In a way, it's catalysis, and probably catalysis is actually this, by the way. A lot of people don't know actually what catalysis is. It's like they say, oh, you start off with this thing here and it interacts with this surface of this thing, and then some magic occurs and the energy is returned, right? Because they don't like any net gain. But I think the energy is coming from the open system rather than the closed system, if you know what I mean.
Yeah, perhaps. Yeah, they say catalysis is an agent that is part of the reaction, but it then leaves the reaction. But it's difficult to imagine how a catalytic surface can react. I mean, if it's part of the reaction,
well, I mean, some of them say
maybe it dissolves from a surface.
Well, in some catalysis, they have like a lot of free electrons on the surface. So they, for instance, in dehydrogenation catalysts, they'll have potassium, which it has a low work function, and it's donating, electrons or whatever. There's an electron interplay there, and that can assist in the process. Now, if you've got a ferrite-based material, and anyway, the point is, I think catalysis is partly this process, actually. And I think when you get to things like cavitation, ball lightning, and well, essentially those are the two things, and they are the same effect. You are getting exotic vacuum objects. These are things that are essentially internally structured on the same pattern of nature, but they create their own bubble of space-time, and they want to feed themselves And the channel through which they feed themselves is destabilizing to matter in our space-time because it pulls too much chi through them. It's not the chi that they want pulled through them, it's the chi that this exotic vacuum object is pulling through them, if you know what I mean. If you over oxygenated yourself, you get lightheaded, you know what I mean? I mean, you can technically do it, but you can even pass out, and some people can die in that process. You know what I mean? If you've ever known about that.
Perhaps not, but I'm open to
There's a
ideas.
breathing technique, and it can be, but
Um,
it can cause elation, but it can also cause, you can knock yourself out. But it's like overdriving the process. It's like, you put nitrous oxide into a car. Yes, it might work, but it might break it.
yep, aligned on that. Well, going back to Hank's experimentation with aluminium, he had an aluminium plate, and I suspect also an aluminium pin electrode or counter electrode. I think it was a rod rather than a pin. It was a way larger setup than, for example, my high voltage experiment setup, which is somewhat documented on the forum. At Hank's experiment, you can see after he runs his high voltage, he simply scrapes the surface of the aluminium electrode, I'm guessing with another aluminium bar, and the huge amount of ferromagnetic material that he is able to pick up
Yes,
later with a magnet.
yes. We had long discussions about that. I have not had a chance to look at that material. I have had a chance to look at, if you remember, he created this metal dome with a thing, a sort of cylinder, and there is a sort of plasma channel that, or something that went through and dissociated the aluminium. There are similar features on that. But I think all of these experiments are indicative of the same process, but I think what you've got there is possibly the cheapest with a capacitor, a couple of bits of aluminium foil, and some deionized water. You've got the cheapest and one of the safest experiments that can be conducted to show the one of the core underlying processes. Like I say, for me, it doesn't really matter that that I've seen it assembling iron that is contamination in the material, in the actual raw aluminium. And we went to the trouble of buying, 5 9s or 6 9s aluminium, but it never showed up. Sometimes that happens with supplies. And so we haven't been able to run that test. But I have no doubt that we will get transmutation in the ultra system because it is a resonant system. But being able to, the next thing I would like to see is a large amount of that iron-rich crenellated spheres produced, because I believe that they have an inherent localized magnetic field still embedded into them. Certainly the ones in Binger and Huang's reactor over the best part of a year didn't even show a single sign of any form of rusting. Okay. And the way that the Chinese originally discovered that oxide, if it is in fact that oxide, because it's not rust, it doesn't look like any normal type of rust. Rust is these little plates, in an SEM EDS, you can't see the hydrogen, so you only see the oxygen and the iron, so you can be confused. But the rust actually takes on a certain crystal form, and it's not those crystal forms. Plus, rust isn't typically bright and shiny. And this material is bright and shiny. And bright and shiny is a way of telling you that there are a lot of free electrons on the surface that the light interacts with. And so if this is genuinely the same material, it hasn't got this, I think, what is it, 270 gigapascal? I don't know, it's some ridiculous amount of pressure in a diamond anvil, and it's 1700 degrees. Now, well, the 1700 degrees might be a way of thermally getting the material plastic, and the pressure is a way to confine it so that it has to reorganize its crystal structure. Well, you don't have to have the temperature to get this plastic because it's become plastic because for the same reason the water disassociates non-thermally, the metal bonds, as we've seen in various types of metal being affected by this process, which is related to the Hutchison process, the metal starts to flow, and when it's flowing, it can then go into these magnetic cores, and the magnetic core has unimaginable pressures. You don't have to worry about those kind of hundreds of thousands of gigapascals. It's way beyond that. So it could be a way to look to mass produce these things. So I think probably the most exciting experiment I think you could probably explore, and I would encourage anyone to do this, would be to try and see how many of these things you can produce, right? Collect them, put them into a very small Petri dish, right? With some water, and put that water into sunlight and see if you can create hydrogen.
Okay, that's an interesting variation.
Because this is what I'm saying. The Department of Energy was trying to look at FeO2, this new high oxidation state, which is a magnetic state of iron, in order to, because of its nature, they suspected it would be like an electron scavenger, and it in ordinary sunlight, I think I'm right in saying it would lead to dissociation of water. But the problem is, how do you make this stuff in any bulk? Well, using ball lightning to create these things in bulk, then you could basically have a passive layer of this with water, and it makes a different type of solar panel, because the solar panel would directly create HHO.
Well, hold this thought a little bit about making these things in bulk. I was also Googling around. I've done reverse image search on these spheres, and I was looking up articles that mention anything similar in industrial processes, chemical processes. I knew electrode discharge machining was similar, and I was looking into that. And I also knew that metal nanopowders are being synthesized en masse at large scale for metal 3D printing. So I was looking around if I could find any SEM imagery of similar spheres that might have these surface morphologies.
Well,
But
it's mostly micrometeorites.
Yeah, I found several articles with micrometeorites.
Yeah.
But I found a few, and maybe we can look over these together at some point.
Mm-hmm.
I found a few that are they are looking quite similar, but is perhaps not Evo related. Maybe it's Evo related. I don't know. It certainly has the possibility of this hypothesis of extreme shear of charge separated material.
So what was that in?
It could be. So, for example, an article I just looked up and I posted it on the LNR forum was mentioning meteorites and was gathering lots of these spheres from, I think, some grinding process.
Mm-hmm.
And they might be similar. Initially, when I looked these articles up weeks ago, trying to provide myself a counter hypothesis for how these spherules are created, which is not which does not involve EVOs, condensed plasmoids, and anything exotic. And now I've relooked at these articles because my SEM imagery turned out to show these features, and it seems that a grinding process also produces these.
Well, if you recall, when I went to India to visit Suhas Ralkar, I actually did a video of someone grinding knives in high-speed photography. And I kind of suspect because what you have is you have a highly intense energy process and highly localized, and you are smashing that metal apart, and it even looks similar, if you know what I mean. And so I wouldn't think it. I would expect it to have sometimes producing the same effect. Are you with me?
Yes, I could imagine it as well, especially if one talks about terahertz phonons. If you grind a metal, maybe you are producing those terahertz phonons, and consequently, probably you're producing EVOs near the surface, and maybe you're producing also plasma because of high temperatures and dusty particles. So I don't know. It's all forms might have the same fundamental mechanism. But
Yeah,
for my experiment,
that's my hypothesis. I start from does it have magnetohydrodynamic shear? And it doesn't need to be high temperature. It just needs to have charge separation or ionized or ionized polar materials in there. That is sufficient for it. The difference is when you get the hollow structures. A lot of these other processes, they don't tend to produce the hollow structures, if you know what I mean.
Yes, and hollow with a specific chemical composition inside, right?
Well, inside it can be depending on when the music stopped, as it were. So yeah, often it's carbon, like this guy. It's carbon coming out, right? But if it pushes it further, like in Bincha and Huang, we had one that's broken open and it's got titanium oxide in there at 22%. So titanium at 22%. And titanium is carbon and oxygen. So if you get carbon, you take another alpha particle because you're running out of space and you need to compress it, you're going to get carbon and oxygen. But if you then fuse carbon and oxygen together, you get titanium.
Yep. I have a suspicion it has to do with how white or gray the EVO is.
Well, I think it's how much it is in a state where it's still receiving matter and energy. So if it doesn't, if it's just a one that's, so I think the best example is to look at SV Adamenko. SV Adamenko starts off with, let's say, a pure metal target. Any metal target will do. Typically, he used a lot of copper, but he did use every metal, and every metal produced all of the elements in the periodic table. But what he got when he did those 300 joule dielectric barrier through aluminium oxide discharges through a light hydrogen atmosphere into the pin target is he got this like banana peel pulled back, and both on the inside of the 5-9's pure target and on the 5-9's accretion copper disc, he would get ejecta, and he knows they're coming from the target because the ejecta have a head and a tail that are all fanning out from the explosion of the target. And what he found is that this particular one could have a certain amount of gold in it. This one could have a particular amount of lead in it. This could have a particular amount of calcium in it or whatever. There are, different mixes. And the way I look at that is that different ones had a different level of compression in that subfraction as it was both produced on the initial compression of the impact and then spread out. But if you go and look at his 2003 patent, in his 2003 patent, he shows a copper accretion disk. And in that copper accretion disk, he shows a hollow iron-rich crenellated sphere, 50% segment of it. So like the top is broken off. And inside it has a perfect hemisphere cut out of the inside. And in a 2005 paper, he says that he suspects that the nuclear reactions to the other elements occur inside that hollow space with the aid of dark matter. Now, I read that a lot longer after I came up with my personal views on these things. Obviously, he'd said it beforehand, and I like the way things occur like that. But it really is, out of 10,000 experiments, it's the image he chose to put in his patent. And it is hollow. It's got a fatter boundary than the typical structures, but I think in his situation, they're not idealized circumstances for the exotic vacuum objects. They are what comes out of the most intensely chaotic process. And if you look at, I've gone on to Lenoforum now into your blog, and I can see, meteorites are producing a selection of random shapes, some of which have reasonably nice boundary areas. And I can see the same is true to a degree.
And do we have a lemon in one of those pictures?
Yeah, right. And that is when the torus is in, it's not quite in the proper alignment, if you know what I mean. Yeah, so I mean, and the thing is, your experiment is so simple. I mean, I honestly, I thought either this would be simple enough, Matsumoto's experiment, and there's only one guy I know since I've been starting to share this, who's actually attempted that, Nikita in America, literally one person on planet Earth. I do know that Luciana has and other groups have done the Ultra experiment and verified various aspects of that. But we now have. Given the provenance and the history of this, the understanding of this process, I think your approach has a good chance to be a very good lab rat for people that want to see sparks. Because the great thing about Ultra is you don't get to see sparks, and there's nothing flying into your eyes, and it's sealed, and you can walk away from it and come back when it's over. But some people like to see sparks.
It's more spectacular.
Yeah, they like to see sparks.
Yeah, the reason I tried this experiment at low voltage, ultimately, I've seen clues at the high voltage approach, which is dangerous. Little voltage is little energy is involved.
Yeah.
But at the high voltage experiment, I can clearly see the shape of the current. Okay, it's a damped oscillations, maybe a couple of pulses, a positive, negative, half period, maybe another one, and it dampens out. But during high-speed photography, you could see maybe 10 or 20 explosions in the duration of one pulse. So you can see a current which has one or two half periods, and you expect, okay, those half periods produce at one area one explosion, because a plasma channel forms at one location and it dampens out and no more. But you can see many explosions simultaneously. So this gave me an idea. Also, looking at the plasma impedance being very low, it gave me an idea. Okay, let's try it between two foils with a high voltage capacitor charged, and I just with my hand and some gloves, I took a capacitor, charged it up, and discharged it, and observed the same effect. The next step was, of course, get a low voltage capacitor and do the same, and the same effect. Okay, smaller crater, smaller dents, but still at 24 volts, 20 volts, upwards to 20 volts, it produces the effect. At 30 volts, it's very reliable if you manage to manipulate the foil to not have any edges that curl downward and touch the other plate. And yeah, it seemingly produces spheres.
That very nice video you took, that was with the 30-volt capacitor, was it? Of the spheres aligning.
I have a small GIF and a corresponding also a small video.
Yeah, I downloaded.
Which shows the process from start to finish. You basically take two foils, add some water, then discharge a capacitor on top of that, and you can see multiple discharges at seemingly random locations and simultaneous discharges, not where the leads of the capacitor touch the electrode, but at totally random locations. It's reproducible, and that particular example of which I made the GIF is also, I've chosen particularly that one, maybe with the hope that you might see it and you might show some interest for it. That particular example with the two groups of spheres, it sort of looks like a fractal toroid is landing in that area, quite large one. The middle of that toroid is where the lead touches the foil, and then you get these two plumes of plasma, maybe speculatively speaking, as if two subtors of the higher n level tor, two n-1 level tors die on top of that surface, and subsequently their n-2, n-3, and all those levels die and produce those spheres. It's just speculative. The other foil examples did not show this pattern, so that's why I think it's just maybe a coincidence. But anyway, I'm happy to share this with the community. I'm not particularly sure what exactly happens. You are certainly the expert to tell. And maybe another note, the reason I looked into these spherules as a product of abrasion was maybe if abrasion produces lots of these microspheres, then it's very easy to contaminate something with those.
Oh, for sure.
I was very careful to do a clean experiment, but it's always I always look at presented hypothesis as an engineer. I always want to challenge it, not to disprove it, but to reaffirm the hypothesis.
Mm-hmm.
And also to have a good understanding of it, so I can think about maybe ideas on variations of an experiment to further dissect the hypothesis and test it. So yeah, once it's maybe it's documented enough so people can replicate. If you
Oh,
think something
I
is
think
missing, you
it
can
is.
instantly.
And you've learned my issue, which sometimes it can take a lot longer to write up your experiment or to analyze it even than it takes to actually
Then do it.
conduct.
Yep.
Um, yeah. So yeah, no, I'm well aware that any process that has charge separation and high energy can produce these things. It's just like the panic set in with uh, um, George Howard when I found these structures on Malcolm Bendel's thunderstorm generator. And the structures are very specifically in regular arrays. And what happened was is I said, well, if this is doing this, it should have these regular hexagonal arrays. And in the back of my mind, it was because I'd already seen these regular hexagonal arrays in Matsumoto's work. And I predicted that if it had those, then there would be iron-rich crenellated spheres in the center of those hexagonal carbonaceous structures. And so this wasn't guesswork. This is based on, experience. And so when he said, "Oh, I've got this thing and I've just cut it in half," and I said, "Stop it! You're contaminating it. Let me come over there." And then I take some macro photography, and lo and behold, it has all of these hexagonal um, uh, darker spots on it. And I say, right, well, now you're going to need to give me a section of that. And they look like this. This is Matsumoto's.
Yep.
Right. And so they look like that. And so I say, well, now you need to let me look at it and look at it under the microscope. And in the center of each of one of these structures, it has an iron-rich crenellated sphere. And everything's at the right proportion. You know what I mean? So it's different from saying, oh, you've got random contamination and it's aggregating to here's a hexagonal spot, and in the center of this one, it's got an iron-rich crenellated sphere. And then there's a whole array of them, and they're all like self-organized into an array. And in the center of each one, there's an iron-rich crenellated sphere. Like it's like nature's probably trying to tell you something.
Yeah,
and
it's in
and
your face.
it's in your face. And so exactly. And with this, I love to see this image where on the February 19th that you shared of the spheres linking together into a magnetic chain, because I saw this with the Nova reactor experiment material that we recovered in 2016. And if you recall, that was the very first time I saw these iron-rich crenellated spheres, and I hadn't noticed at the time that one was hollow, and I hadn't noticed. I mean, because one was 250 microns across, it was absolutely massive. It's difficult to see the crenellations on it, and the camera, the SEM that I used, wasn't that good at the time. However, what I did notice, they seemed to be aligning as if there was a magnetic north and south to each of the spheres, right? And yeah, this I'd seen in the Lion reactor in 2017, where some spheres had, and it was weird because you had the outside of the reactor and 50% in to the fused quartz, there was a sphere half in and half out. And then there was another one bound to it, and I can only assume it was magnetically. And then there was another one bound to it. So there was three in a row. Like it all come out of the same coherent matter core, and it dumped a selection of spheres as it progressed, if you know what I mean. But it was disrupted by going through the impedance change of the inside of the fused quartz to the outside. It was neutral, and then it became excited on the boundary. And so when I'm looking at your video there, which is beautiful. So I did ask it earlier, but I think you misunderstood me. Is that video that you're showing, was that from the low voltage experiments without any iron? That is to say, you used copper leads on the capacitor.
Hold on a second. I have many videos and
So
GIFs.
I'm talking about
Which
the one
exactly?
where you have a GIF and it's a GIF, and you've got a piece of copper, and you are moving around a selection of spheres. You shared it on February the 19th.
Oh, manipulating the microspheres under the
Yes.
microscope.
Yes.
Yes. Well, to explain to you and perhaps to an audience, that collection of spheres was painstakingly gathered from multiple experiments and from the entire surface of the magnet. And once I realized that they happily join and align to the magnetic field lines, it occurred to me that those are the ferromagnetic spheres, and those are not aluminum spheres. Those are something else, ferromagnetic, iron, nickel, whatever. And that was the point where I encouraged myself to try to get an SEM imagery of it.
Mm-hmm.
So that picture is on a magnet. On top of the magnet is a paper tape. By the way,
Right.
don't ever use paper tape. Use maybe a Teflon tape with double sticky tape on top of the magnet, or something much more smoother and which releases easily from whatever carbon-based carrier you're trying to transfer to and put it under the SEM.
Mm-hmm.
So that is a magnet, on top of it paper tape, on top of it the captured microspheres and painstakingly manipulated together with a needle, with a copper wire.
Mm-hmm.
First I tried the needle, of course that was ferromagnetic, and the balls just bounced all over the place, and I lost spheres, and I had to spend many more hours to find other ones.
No, that's great. So then they're not magnetic in their own right. They're just showing ferromagnetic and aligning with the magnetic field.
Well, if they are iron-based,
They'll
are
probably become magnetized after a while. Yes.
No, I mean, if the microspheres are ferromagnetic, they
Yes.
will align.
Yes. Yes.
Yes,
Yes.
and if they are iron-based, then they have a high chance to be ferromagnetic.
Yeah. Yeah. Great.
So, what was the question again about that video?
Oh, it was just I wanted to confirm that this was produced with the capacitor and aluminium and deionized water, with the capacitor with the copper leads, rather than, because you said the initial one you forgot that you probably had steel leads on the capacitor.
Yeah, well, that one where you can see the sphere grouping manipulated by a copper wire near a strand of hair.
Mm-hmm.
That one was that was actually the first attempt to gather spheres with a magnet, and the normal leads of the capacitor, the low voltage capacitor, was involved, which was ferromagnetic. And also I also scraped off the high voltage setup, which was not clean. It was not carefully used to avoid ferromagnetic materials. But after that, the latest post, when you can see the SEM image, and also you can see an optical image, optical microscope image next to it, with many groups of spheres. In the center, I've marked with a Sharpie, with a black permanent marker, 4 dots, and I pulled in that square, in the middle of the square, I pulled in a group of ferrules which were obtained by low voltage setup. So a low voltage capacitor with copper extensions soldered to it, so nothing ferromagnetic was touching the the aluminum plate during the discharge or during whatever time.
Yeah, and I see
So
there's
it
several.
could
It
not
also
be.
looks like you got some silicon dioxide ones there, which is what I also got in the 2016 uh, supernova or nova experiments. You typically get silicon dioxide or uh, you mostly appear to have two sizes there, apart from the bigger silicon dioxide one. You've got
It looks like a quantum. It also was occurring to me, and I was thinking about it. If these EVOs, condensed plasmoid, fractal toroidal structures, uh, if they have a build as a building block a background neutrino or
Mhm.
LC dipole, and they construct upon those LC dipoles as fractal toroids,
Mhm.
then you should have quantized levels of these sizes
Oh
of
yeah, yeah,
these
yeah, yeah,
toroids,
yeah.
and the output of the one of these toroids, when it collapses and it emits the captured mass. Well, also thinking about the level of excitation or the level of captured elements, which means uh, gray, how white the EVO is, right? Uh, these two things, I think I was imagining the size of the toroid is quantized, and the level of mass captured in those very strong fields.
Mhm.
That might not be quantized. You can have a fine granularity there, but if you were to obtain a very narrow distribution of size, then it's probably an indication that you're energizing these evos, you're creating them in a very similar fashion, you're destroying them in a very similar fashion, and they have the similar size or same size quanta, and they're outputting the same size spheres.
Yeah, so what I'm looking at here is Nachamkin's paper on ball lightning actually says that, and they're only looking at the outside structure. They're saying that that has quantized stable states, and that fits with the hypothesis that the fractal toroidal structure internal to that, which I believe drives the outer spherical shape, is also quantized. But there's a ratio that we know exists, which is roughly 1 to 4. And I'm roughly seeing it in this image that I'm looking at here, 3 of 14, that you posted today and sent me separately, where you have the what I would say was silicon dioxide predominantly, smaller spheres, and the larger spheres are the FeO two spheres. There is these anomalous, very large silicon dioxide sphere and stuff. But here's the thing. As I was saying to you earlier in our conversation here, I believe that if you have a pulsed one, they form standard shapes. But if you have one that's generated and then fed and fed and fed, uh, it can continue to build substructures. So the minimum one is 2, but if you have more substructures around it, I believe it can then synthesize heavier elements at the various quantization levels. But what I see,
All right, right.
are you with me?
Yes, yes, yes. Now that you explain this, it also it's not a two-level subfractal structure. It can be 3 or 4, 4 being stable because the
Yeah.
disruption zone is within
Yes,
the
yes. It
boundary.
starts to be within the other one's non-radiating boundary, and then at 5 it gets further in. But when you get to 6, it's fully within the apple on the sub layer, and that makes it very very stable. And you've got to be careful because when the matter that's in these overall structures settles out, it settles out often into a crystal structure when it's not in the spherical cores. So, for instance, you get, but even in that case, in the work of my analysis on the thunderstorm generator, you see 5 and 6 shaped carbonaceous deposits with the iron-rich crenellated sphere in the middle. So 5 and 6 is enough to create iron in the middle. Now, is 4? I don't know. Is 2? I don't know. But there's one where we see a blowing up of a large ball lightning in Henkurian. You have the vortex coming in, and then you have the top of the caduceus, and then you have the big iron-rich crenellated sphere, and then you have the subquanta, which are not iron-rich crenellated spheres. They look more like silicon. So I think what you've got in that particular image, where you've got a group of 3 iron-rich crenellated spheres that are approximately the same size, I would argue that those are the same overall stable subquanta with how many however many subquanta they had round it. But looking at the two, uh, what looked to me, based on my experience with looking at the stuff in 2016 in the Nova reactor, the spheres, the smaller spheres, which seem attached to the bottom left and next one up to the right, they look like the subquanta. And if you go and look at that one of Henkurian's, the big sphere actually has one of the small spheres attached to it in a very similar fashion to this.
Yeah, very, very good finding.
So I think
the good news is
go on, sorry.
the good news is the low voltage or the low voltage setup also produces a variety of.
Well, I'm looking at that low voltage. I'm looking at.
Yeah.
I think that's the grouping.
Yeah.
Yes. So I can see that on the left-hand image, you've got HV, 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 2, 3, and 4, and then there's a square box with low voltage, and that grouping is the grouping that I'm seeing in that next shot.
Yes, exactly. Yeah, I was under the impression that maybe the high voltage approach involves higher energies and it's able to create larger quanta of EVOs, and maybe those EVOs are able to capture more material and they can output a larger sphere.
I think it's resonance.
Yeah.
You'll get it snap to a structure that can do the work. And also, you've got to bear in mind you're feeding it predominantly hydrogen, oxygen, and aluminium. And aluminium is, if you take aluminium and you fuse 2 aluminiums, you get iron 54. So there's very little effort to get to the iron if you're reorganizing nucleons. If you want to get a silicon from that, you just add the proton. So that's even easier. So the idea that you're getting silicon and iron are fairly trivial, if you know what I mean.
Yes.
And then the question is that iron actually, when you look at it, and this might be another reason to produce a lot of these microspherules, is to then put those produced microspherules into an ICP-MS and see if it's predominantly iron 54. If it's not, then you could argue that the natural ratio of iron comes out of this natural process, which is ball lightning, and that is how everything is made, whether you can see the ball lightning or not. And that it's a case of some of the protons are combining with some of the electrons that are always associated with every proton that exists in ordinary matter. And they are with the dark matter, in the case of relic neutrinos or clusters thereof, producing neutrons and yielding the other isotopes, preferentially of iron. So there's a lot to learn when you can produce these spheres at a sufficient quantity. But the idea that you're seeing out of water, which, remember, you've always got the oxygen there, and the oxygen there is the binder for the clusters, in my view, right? And it turns out, prior to my view on that, I mean, my view stems from the 1996 work, 1996 work of Sundaresan and Bockris when they did a replication of George Osawa's experiment underwater. They deoxygenated and denitrated nitrous. They removed all the gases from the water by boiling it, and then they put nitrogen in and saturated it nitrogen and put oxygen in. And the one with nitrogen produced zero extra iron. But the one with oxygen in produced extra oxygen. Sorry, extra iron, right?
Okay. Hold this thought a bit. I have a question related to this. So at Hank Uring's Vega experiment with aluminum plates, he's using a vacuum system, right?
Yes.
Plasma glow discharge,
Yes.
arcing discharge in a plasma in a vacuum environment. No water involved, right? No oxygen gas involved.
It's not a very good system. There will
But
be
wait.
residual air in there, and there will be residual moisture in there.
Hold on.
Go on.
Aluminium oxide.
Yes, of course.
On the aluminium electrode. So,
yeah.
I'm thinking on a variation of the experiment where I would mash up some aluminium oxide in a powder dust form, and zap it with these high currents and see if it produces these spheres.
It's definitely worth a try. Here's the thing. In 1980s, I think 87 or 89, Yul Brown demonstrated, and it might have been in a news article, he was reporting demonstrations that he had made and that he then later made in the US, but it was in the 80s. He remediated various nuclear isotopes, and he did that by adding aluminium shavings and iron shavings to the radioactive material before applying the HHO gas. Now, we know the HHO 100% can produce the magnetohydrodynamic structures. And he says basically it starts to glow brighter, and then there's a flash explosion and the radioactivity is gone. And I view that as loads of little clusters are forming, and they are consuming the paramagnetic aluminium and the oxygen that's available. And the clusters are binding to the iron. And they're all binding to the iron, growing and growing and growing in intensity as more of this special gas is coming in that has this special component in it. Keeps coming in. So they're building and they're building and they're building. And then what happens? It thermally goes through the Curie point of iron. And every single one of those clusters are released at exactly the same kinetic energy and exactly in phase. And they all snap immediately together into one macro ball lightning. And because it's already got the nuclear material in there, the matter collapses and the radiation is gone. I described this in my video to the Russian community in 2019, maybe. It's called monopole clutch, and you go down to the Yul Brown, but I believe that is what is going on in Yul Brown's nuclear remediation. So, just to be brief, it forms the microball lightning. They are sucking in by disassembling the atom bombs in the radioactive material and pulling them into the cores. They're building up and building up, fueled by the aluminium, fueled by the incoming HHO, the shear, the plasma, and so on. But they are, with their own same magnetic moment, binding onto the pieces of iron. And then goes through the Curie point of iron, and they all snap together, one coherent matter that collapses in, nuclear material is gone.
That hypothesis, I think, reminds me of it was it Piantelli who mentioned going beyond the Curie
Oh
temperature?
no. My time with Piantelli helped me understand how parts of this process occurred. So I've explained this from the nickel point of view. He told us we must go through the D by D by D by, go up and down, up and down, up and down, and load that nickel up as much as we possibly can. Now, I have since thought that that is because you're using nickel's a bit natural ability to catalytically, there's that word, split it into atomic hydrogen. Now, he believed it was H minus, so a proton with two electrons. It doesn't matter because anything other than H2 has a magnetic moment. That's the key thing, right? So let's say we've got a sea of electrons on our metal and we got the protons. And then he said the key to the process is to go through as fast as possible the nickel Curie point. And he never explained why, but I've argued this since in various videos that in my view, all of your protons are sitting in a sea of electrons, and they are immediately released at exactly the same kinetic energy and in phase because you are going through the Curie point as fast as possible. And I believe this explains, and I've argued this before, why in 2013, in October 2013, we saw some form of radiation. We called it gamma. You can go to the old quantum heat website and look at it. It's called gamma. And what was happening then, we had a Geiger-Müller tube outside the reactor. This tube, which I've got in the other room actually, leaked and it went from its supposed operating pressure that we were replicating Chelani at 3 bar of hydrogen down to atmospheric because of the partial pressure and the leak. It was just leaking to atmospheric pressure. And we used a little mini can to re-put hydrogen in. And how I conceptualize that in my brain is the fresh hydrogen is coming in and hitting the wire. Now, hydrogen coming out of a can goes very, very cold. So it was flash cooling the wire, the whole wire. Hydrogen has the highest thermal heat capacity of any gas. And so it's massively cooling the wire. So the whole wire becomes very cool, yet it's still at its operating power. And so what happens is, as it warms up, it disassociates the hydrogen, they magnetically bond to the nickel in the constantan wire, and then it got released all at the same time. And it then produced this coherent matter clusters. They then were effectively dark ball lightning. They went through the gas in the rest of the chamber, through the borosilicate glass, through the plastic, through the metal chamber, inside the Geiger-Müller tube, and caused it to have a tripling of the background radiation for about 90 seconds. And this was repeatable. It was just repeatable. And later on, we were told by the Russians that when they took their powder reactors, where they had a large volume of powder in their reactor, and they heated it up and then they put fresh hydrogen in, they got what they call their whole labs filled with strange radiation. And that's when they stopped doing their research because of the death of Yuri Bajatov. And this reminds me of what happened to Thermocore in the early 19, I think even 1990 or maybe 91 or 92. They had something like a kilo of nano powder and they had a meltdown event, although they had no thermal detection on the outside, but they saw orange spots on the outside and the thing broke. They had fresh hydrogen going into heated nickel powder. And I think exactly the same thing occurred there, except they formed a macro ball lightning that did what macro ball lightning does in our experiments. It produces a tornado, and the tornado came out so much chi through it made the outside of the reactor orange, but it wasn't in the thermally orange temperature. So there's so many instances where this similar process is occurring. And so, yeah, basically.
Yeah. We also touched strange radiation.
Yeah.
And maybe it's worth mentioning if you intend to
Yes.
replicate these sorts of experiments, there might be a risk to it.
Yes.
Well, on one side, I hope this simple approach with the low voltage capacitor will be replicated and people will perform some EDX analysis, and maybe I am maybe if we can find some friends with a high-speed phantom camera, I would be very
Well, I don't put
interested in
your
looking
needs
at
that.
those parts.
I think you're going to learn a hell of a lot from just good, even with the Sony Alpha that we have. It only does 120 frames a second, but it'll do that at 4K and it'll give you spatial resolution, but it doesn't have the rolling shutter that you're suffering from. So you get like half of your frame exposed because it's wiping down that.
Yeah, yeah,
You ideally you want a global shutter,
yeah.
and you
But think about it. Maybe 1,000 frames per second with
yeah,
a
yeah, yeah. Oh
rolling
yeah,
shutter is better than a
of course.
120 global
Of course.
shutter.
Of course. The beauty of what you've got there is it's predictable. And because it's cheap, and if you're willing to sacrifice a camera because it might damage the CCD's elements in there, but or the lenses, that's something that people need to be aware of. But you can keep running it, and with a lot of these cameras, you can actually for instance, the Sony Alpha can take 30 frames a second at 50 megapixels, but you can set it so that it takes 1/20,000th of a second exposure. Now, it might miss several discharges, but if it hits on a particular discharge, you can get the nose of the lens right in there at really incredible resolution. And you might be able to dig in with the high dynamic range, the 14 and a half stops or 13 and a half stops or whatever, to see through the plasma and actually see the substructures in there, like we've done with Henk Uren's experiment. But in Henk Uren's, we've had to be, half a meter away from the action. Where with this, if you're willing to sacrifice a lens or two, you might be willing to get, right down and into the event. So I've said for years, there's a whole blue ocean of opportunity here to do real groundbreaking science and to understand what's going on in this process. And I have to thank you for having the courage to combine a couple of your ideas together. And what I'm looking at the frame here, this image from your posting today from the low voltage, this gives me a lot of great hope that people are going to be able to see some very nice science coming out of this.
Yeah, well, I'm happy to be able to contribute if any I try to drop in the ocean. But
Don't you
I,
do
I
yourself
I
down.
think
It's the people
I
that
think
do.
you're with the blame. You don't have to thank me. I have to thank you for putting all the stuff out and informing people about this.
It's a case of mutual respect then, because there are few people that actually go ahead and do. And what you've done here is you've done some doing. And with the Ultra experiment, it was at a level where it was literally child's play. There's basically zero risk that someone wouldn't be exposed to ordinarily in their lives with things they have in their household, if you know what I mean. With this one, there's slightly more risk, but actually the cost is quite a bit lower for the experiment. And if it's able to produce the iron-rich spheres and the silicon spheres um, more reliably and quicker than is an experimental lab rat, it's fantastic. So, could you give an idea of how much the capacitor cost and just reel off its specifics?
A capacitor. Um, Maybe it would cost nothing if you unmount it from whatever old electronic equipment you have, an old power supply or something. If you buy it new, I don't know, maybe 10 pieces would cost you a couple of dollars.
Yes. And
Quite
the
cheap.
aluminium foil people have probably got lying around their house.
Yep. Distilled water I've used, which is maybe uh, $2 tops
Yeah,
a
probably
bottle.
couple of euros or something. Yeah, the same sort of stuff. Yeah, so I mean, it's very affordable. The most difficult part is to have access to an SEM with EDS. I expect my colleague Alan is perfectly able to replicate this experiment if he sets aside a couple of hours of his day, and maybe I'll reach out to him.
Alan Goldwater.
Yes, yes, yes.
Yeah, well, he promised me he might do it by the end of the month.
If he wants to do something, it'll probably happen a lot sooner than that. So maybe I'll give him a shout. It'd
Okay,
be nice.
maybe we want to touch on perhaps a few details around this experiment. So
Yeah, go
things
on.
that are not mentioned in that GIF, that
Yeah.
DIY guide.
Okay. Yeah, go for it.
So I think that that DIY guide GIF explains what is done. The question is how many of those things you need to perform, how many times, and what is the procedure to gather the spheres in order to obtain a couple of spheres that is worth putting in an SEM. So I've used maybe 24 of foil pairs. So a pair is a larger piece, which is the anode, and the smaller piece goes on top, which is the cathode. And of course, cathode emits electrons. I thought it was easier to jump electrons from a smaller piece. I haven't tried the other way around, but you can try it. So maybe 24 of electrode pairs. And the way I do it is I have the lab power supply set to 30 volts. I have two leads coming down on the table. I take the capacitor, touch it to the wires, the crocodile clips that come from the power supply, charge it up. It produces a spark when you charge it up, of course, because you have a high inrush current from the power supply's capacitor into the outside capacitor, and there is no limiting inductor or resistor in between, but you can use a resistor. Not important. What is important is when you charge the capacitor, maybe you want to charge it. You want to solder some copper leads to the capacitor to make sure that you're not playing with ferromagnetic leads. Mm-hmm. And when you charge it up, make sure that you don't charge it up by the ends of those copper wires, touching maybe ferromagnetic crocodile clips or whatever you might touch it to charge it up. Then, once it's charged up, you just gently lower it down and touch on the electrode pair, on the foil pair. You can expect this discharge event which branches out in multiple random places, or you can have at times one localized discharge, which is, let's say, more violent, and you can monitor the voltage on the capacitor. It discharges more abruptly. If you have those localized high current discharges, maybe your aluminum plates are touching somewhere, maybe the ends, maybe you did not curl the ends of the cathode upwards, so the ends could touch the other plate and have a localized discharge and also melting. You can also have, I also had multiple times melting together of the two pairs and not producing any of these craters which look like evil witness marks. Then I didn't discard that pair. I just ripped them apart. They were touching at a single point. Rip them apart with the water on them or between them. Place them down together. Charge the capacitor up again. Discharge it again, and maybe do this 5 times until you have covered the surface area with visibly, let's say, sufficient of these craters. So you can say, okay, let's move on to the next electrode pair. You do this with 24 of electrode pairs. Then what I did is I broke them apart. I took the electrode pairs apart so the water can dry, and left it to dry an hour, and come back and use a toothbrush, a clean toothbrush, scrape every single foil. So 24 times two sides. You need to do a lot of scraping. Scrape it down to an area of, let's say, a working table or a working surface, a clean working surface. I did use a aluminum sheet to work on. Scrape whatever comes off from those electrode pairs onto a clean surface. Then you can attempt extracting with a magnet these spheres. Then the typical stuff, you look under the microscope, make groupings if you want, transfer it for SEM, and do the microscopy.
That sounds very, very doable to anyone, really. I guess that if you didn't have a lab power supply, you could gang maybe 3 or 4 PP, 3 batteries.
9-volt batteries.
Yeah,
You can chain up 9-volt batteries.
yeah, something like that.
That's also cheap.
Yeah, because not everyone has access to a. But I imagine if you're going to have access to an SEM, you're going to have access to a lab power supply.
I think that's the least of your problems.
Yeah, I
But
mean,
even so, if you're interested in this, if you want to replicate and you don't have access to SEM, not even maybe a microscope, you need a microscope. I was thinking about, you can play around with a magnet, and I don't know if you can gather enough of these spheres, maybe scrape them onto a small piece of aluminum, put it on a water bath, try to play with a magnet around it, see if it attracts it or something. I mean, just a basic sanity check that something ferromagnetic has been produced.
mm-hmm.
And of course, you can, in advance, you can double check your materials. You can perform the scraping, and you can check your tools for these spheres with the same magnet or a similar magnet. You can tear up a bunch of aluminum foil, try to shake it, try to scrape it, try to obtain from them contaminated ferromagnetic material, and see if you can find some. And if you don't find some, you can do this experiment and see if you can get some after the experiment. So basic sanity checks.
And for those that think, should I be bothering to do this? What evidence is there that this is even possible? Over and above what I've already said, I would like to draw people's attention to the late Mahadevin Srinivasan at ICCF 20 in Japan, and it's going to be ICCF 26 in Japan in May. But at ICCF 20 in Japan, he shared some data that he'd been sitting on for nearly 2 decades because he feared for his reputation sharing this more widely. But this was, I think, in Coimbatore. It was I think it was an 11 megawatt, or maybe even more than that, ferrosilicon foundry furnace. And it had these, I don't know, something like a meter thick graphite electrodes, 3-phase. So it's AC. Essentially, when you're doing this pulse discharge, it might as well be AC as far as the water and the metals are concerned, because you're going to get, all kinds of things going on. You talked a bit about that earlier. There was a kind of ringing going on.
I think in any system with a
Yeah,
high voltage
yeah,
capacitor charged up and you
yeah,
discharge it, there's no way you don't get an AC current because of the parasitic inductances.
yeah, yeah. So they had a three-phase electric arc furnace, and they were feeding into it sand, uh, coke or charcoal or whatever, and I think it was coke, and they were feeding in scrap iron. And for an 11-week period, it produced 3 extra tons of
3 extra
silicon.
metric tons of
Three,
silicon, which was not introduced in the system.
yeah, three
Yeah,
extra
I've read it.
metric tons of silicon and 1 extra metric ton of iron per day, every day for 11 weeks. And so the only way that you can get to this situation is, as I said earlier, you fuse carbon and oxygen together and you get silicon. I made a mistake earlier when I said carbon, oxygen, titanium. It's CO2, which you get titanium. But anyway, carbon and oxygen, you get silicon. And if you fuse two silicons effectively, all bar spare change, you get iron 54. But like if you've got a few extra protons in the mix, because maybe you've got some higher amounts of carbon or you've got some higher amounts of oxygen in terms of the feedstock elements going in, then you're going to get the other isotopes of iron. And so here we have an experiment. I'm looking at a frame that was shared by Tibi, and I have to say it looks very much like the same material that I got out of a carbon dusty microwave plasma in 2016, which had silicon dioxide in blobs and shiny blobs look very similar under the SEM and these iron-rich crenellated spheres, which seem to line up to each other. It looks very, very similar. And you have silicon, you have iron, same thing going on here. The feedstock in this case is aluminium, oxygen, and water. And so you have oxygen. Uh, Basically, it's in air, so you're going to have oxygen and nitrogen. But I think the key components there are, well, possibly nitrogen. Nitrogen might account for some other isotopes being formed, but basically, oxygen, uh, oxygen, hydrogen from the water, and aluminium. And so I think it's very likely that this is the process that's occurring. What can I say?
I'm happy for it. It's the first time I see with my own eyes
Yeah,
something this interesting. So for me, it was an important moment when I looked at the first SEM image, and
yeah,
I've seen that typical sphere with those brain-like structures or orange peel-like
yeah.
structures and the triangle structures in it. So I don't know. I think I'm a believer, and I want to.
To,
Maybe
to,
I
to
want
me,
to.
like I say, I find these things predictable and fairly boring now, but I know I have to keep reminding myself that this is extremely exciting and groundbreaking. And I'm amazed that you've done a good job here in getting an even simpler experiment than Matsumoto's and essentially you're not far off from that Coimbatore reactor, but like the whole debate back in ICCF 20 was, well, should we go and build another multi-megawatt reactor and see if we can do the same thing? Well, no, actually, it would appear that you can get the same job done with almost nothing. you know, and you've shortcut the process to get to silicon by feeding it a lot of aluminium. The aluminium is one proton away from being silicon, and aluminium likes to fuse to iron already. So, you've got a really good feedstock there. And when you consider that oxygen's the most abundant element in the crust, and then silicon's the second most abundant element in the crust, and the third most abundant element is aluminium. And iron isn't far behind. Yeah, I think we're getting to an answer here now. And uh, I don't know how people out in mainstream science that believes you have to do X, Y, and Z to create fusion. I don't know how they are going to deal with this mentally to realize that all these experiments have been done over many, many decades showing this. And now it's got to the point where, you know, as I said in Azizi to Konrad Chersky, the head of the uh, uh, Szczecin University research team, I said, all you've got to do is spend dinner money and 7 minutes of your time to find out if I'm wrong. And now it's getting down to a pack of chews. It's not even dinner money. You can't even get a refill of a bottle of water.
Yeah, I'm also waiting for the moment when we can travel faster than the speed of light with materials that you already mentioned, woods and stones, and maybe something like that.
And the funny thing is, it's going to be this process. It's the same process. It's the same fundamental electrodynamics. What you're doing is you'll be creating a different bubble of space-time. And you don't want, and the great thing about our bodies, other than the iron in our blood, is that we're largely non-magnetic and we're not silicon based. And so there's parts of the electrodynamics, I believe, which you can see on the Griffin-Brock electrode and which we've seen in other manifestations of the phenomena, where it's kind of balanced out the field structure in there so that you could, in my view, safely be, and the magic could go on around you, and you're impervious to things that will ordinarily cause all kinds of strife for someone that's made of meat. Yeah.
Wait, hold on a bit. Baby steps at a time. I told myself if I read a lot about EVOs, condensed plasmoids, fractal toroidal structures. For me, this was my hobby, so to speak, to read about this stuff. Okay, and I told myself I must see it in person. I must create an EVO. If it's as easy as a spark discharge, then I'm gonna do it, and I'm going to look at it.
This guy said it in 1996. In fact, he said it in 1991. He said it in 1991, but when he started to mention ball lightning in 1993, they changed the rules so he couldn't publish. So I'm pretty sure someone knows that this is how it works.
Yeah, well, if it gets as simple as freaking aluminium electrode pair from the kitchen and a capacitor, or even simpler, then it will be difficult to stop anyone looking at it, right? And publishing or not,
we've been in a position since 1992, certainly since 1996, with Sundaresan and Bokras, and with this, and the fact that Srinivasan knew all the time back then about that foundry in India. There were people that knew how absurdly trivial this is. But with the ultra experiment and this experiment, it wasn't enough. But I'm gonna throw down hard now. It's getting to the point of gross negligence of the entire scientific community outside of the black world to not investigate this. Gross negligence on the sake of humanity. Just the ability to synthesize key structural elements like silicon and like iron from essentially water and aluminium. You just the potential. It's not necessarily that you gain the potential energy in this particular state, although very specifically the extra thermal heat gained in the water of Sundaresan and Bokras in 1996 or whenever it was in the mid 1990s. It was exactly the same as the production of iron from the original materials. Now, they calculated it was carbon 12 plus oxygen 18 times 2 goes to iron 56 plus alpha, but they plus helium, but they didn't look for helium. But if you do a different equation where you get four protons, four oxygen 18s going to, so it's oxygen 16s going to four oxygen 17s, and those all fusing and then fissioning to 12 carbon and iron 56, it's almost exactly the same amount of mega electron volts and would account for exactly the same amount of synthesized energy produced. And so their data alone proves that you can get thermal yield energy from this. So yes, boiling water reactors should be possible with this. And that's when you're using water. Of course, the Coimbatore reactor didn't have, it wasn't majority water based, it was majority other elements. And, you know, some of the elements, because of the way it was configured, it might have just been less electricity that was used to get everything working together, and they weren't really clocking the amount of electricity that was used, if you know what I mean, because the figures are about the excess metal, not the lack of electricity used.
Okay, well, I have to ask something.
Go on.
So the background of this sort of experimentation is, of course, was George Egely coming out with an handheld apparatus claiming it produces excess electrical energy through LNR. And I said, wait a minute, I'm an electrical engineer. I'm going to reproduce this. So I had an attempt on reproducing it. I think I reproduced some macro effects, but I could not see signs of excess electrical energy. Of course, I did my own variation of the entire experiment, but jumping into a complex system with a repetitive discharge and trying to find a net output which is
it's really
suitable
hard,
for me was, yeah, it's hard. So I dialed it back a bit, and I said to myself, well, if I'm going to see something, I must investigate the fundamentals. That's why I challenge myself to investigate single discharges that produce maybe higher currents, and that led to these fears. But so to speak, I'm not happy with spheres. I can do nothing with these spheres. The next
to do it. If you get enough of them, they might be passive under normal sunlight dissociation of water. And if that's the case, that is an unlimited energy supply. Storable.
Yes, but let's say we don't want to produce, we don't want to use sunlight, we don't want to produce hydrogen and store it and these sorts of...
Yeah, but the beauty of that is you can use a proton exchange membrane and directly produce electricity from it later. You separate out the light fraction, you store the hydrogen, and then you can use that with a proton exchange membrane to produce electricity.
Yes, for that I need a proton exchange membrane, which is not a household item, which I would like to play with household items like this experiment.
Yeah, I
what
agree.
I want to ask is, as a continuation of this experiment, we know aluminium plus aluminium can turn out to a lower atomic number iron isotope. What would be the combination of elements which can yield excess heat. So the output atomic number is somewhat lower than what goes in, and the excess is transformed in a magical way into something useful. For example, heat. Taking baby steps one at a time.
Okay. In theory, this process will be producing strange radiation flux. Now, the question is, how do you get this process working at a sufficient repetitive rate in order to produce a measurable flux of that radiation? Well, one you could look for the radiation, so you could buy those self-developing X-rays and have a bunch of those around it and see if you get some strange radiation tracks, or ideally the birdies. Do you create the birdies? If you're creating the birdies, then you're creating these topological magnetic monopoles. And they are the thing that do the magic. Now, if you're creating sufficient flux of those, like is likely to be occurring in many of these systems, then you can look at, say, for instance, having a secondary material, which may be as simple as graphite, or it could be something like lithium fluoride, which has been identified by Alexander Parkhomov as one of the better secondary materials for interaction of whatever is being produced in these systems. That would be a way of producing heat. But we already know that the production of iron from carbon, oxygen, and hydrogen produces significant extra heat. And there's a lot of ways in which that can gain heat, in nuclear balance.
Mm-hmm. Carbon, oxygen, hydrogen. Okay, tell me how.
No, I'm talking about the experiment. I'm talking about the carbon arc experiment underwater of Sundaresan and Bokros.
What I'm thinking about is, maybe I've mentioned it before, but as I posted, I think in my first post on the forum.
Yeah.
I intend to explore high current discharges at various materials. And I'm thinking, okay, water is interesting. Aluminium electrodes is interesting. Okay. What about solids, powders of solids? And maybe do it in a high repetition rate, maybe inside the calorimeter, monitor the input energy, put out the energy balance.
The problem is when you're working with any solid systems, you could get a runaway like Thermocore did, or like Pons and Fleischmann did, and then it's like all or nothing. If you're going to accept that there is a fuel and it gets used and it's in an optimum configuration, and then it's not an optimum configuration, then you feed it and like Solin did, you feed it like Bokros and Sundaresan did, you feed it like Tesla did in his electrical particles of matter gun. You effectively feed it like Ken Shoulders did. The problem with, I suggested aluminium to George Eagley, and that came into this reactor that produced over unity of electricity which was verified by Jean-Paul Barbarian. And I trust in that. The problem is with that system is it will produce oxygen at the very least, and carbon as well. And that will gum up the electrodes. And after a while, those electrodes will fail. So it might work for an hour, it might work for half a day, but it's not going to work long term. And
yeah, that's why I'm thinking on a plasma discharge system in maybe a closed envelope with some dusty particles. And the idea is not to, let's say, build up something, not to, as opposed to, let's say, a vacuum metal loading system, when you keep loading up the metal and then you trigger it with some transient. in this repetitive discharge dusty plasma environment, it's the entire cycle from start to finish within one pulse, hopefully, or maybe one pulse. The first pulse creates the plasmoids, and the second pulse destroys them. Make and break. But the idea is to not have something build up, and all of a sudden something
Okay, so
that happens. To have a repetitive small quantity.
Go into Ken Shoulder's work. He says the way you get many electrons is you have to make the evo, and then you have to send out another one a few even nanoseconds afterwards to break it up. And that is how you get the extra electricity.
Yeah, the nanosecond could be honored by high frequency one discharge, which has a high frequency oscillation to it, a damped oscillation, because we've seen a capacitor and parasitic inductance causes a high frequency oscillation. And Lutz Geithner also told us if you reverse the current through this plasma, then you break this conductive path. So that would be the break of the make and break cycle, to reverse the current.
You don't particularly want a discharge that you then stop, like a quenched discharge, like the magnetically quenched discharges of Tesla. Although that is one way to do it. What you want is specifically a discrete exotic vacuum object chased behind by another one that then blows it up. And so you want one to be partially condensed and then the other one to come in. And I believe Shishkin's nailed it, that you release something that then can be produce a lot of extra electrons.
Yeah, but I'm not necessarily looking at producing extra electrons. Again, baby steps at a time. If I see one evo, then okay, then the next step is to produce maybe more evos. Then the next baby step is to produce evos in a controlled fashion that produce not only transmutation of elements but excess heat. I'm looking to heat. That's the simplest way to detect and also perform a calorimetry and put a power balance. On an electrical system, it's more complicated. If it
I think the simplest thing is to replicate the Sundaresan and Bockris. You have carbon and oxygen and hydrogen in there. That's it. So you've got, wherever you're going, you're going to gain a lot of energy by fusion. They produced iron, and they already did the hard work for you to find out that having oxygen dissolved is the key. So you boil the water for a period of time to degas it. You then bubble oxygen through it. You could use electrolysis and choose the oxygen output from that to saturate it with oxygen. And so you're going to maximize the process. And then it's just DC electrical discharge underwater. And then again, you'll be looking for the synthesis of iron. What they never did was look for iron crenellated spheres. So you could correlate the amount, you could put the amount of electricity you put in to do the discharge. You know that because you can watt meter it. It is not so much very high frequency transient.
But I think most of that energy is wasteful. If there is a long duration, high current, I think you'll get just heat out of it. I think what matters, I have a feeling on what matters is a very specifically controlled transient event which triggers the formation of the evos. And then their natural resonance comes in and they start to chew up the material. The rest of it might be counterproductive if you create a hot plasma with that wasteful discharge. You not only throw away your input energy as heat, but you're also creating unfavorable conditions for these evos to do their thing. right?
Well, I mean, you're at a disadvantage because you haven't seen so many videos of Matsumoto's, but a lot of his um he would just have like a titanium rods in water doing discharges, but I've at least shared a couple of these where it's producing the ball lightning. The ball lightning is moving across the surface like it does in Hank Gruen
Yeah,
experiments.
I've seen it. Yes, I've seen that, but mhm.
I mean,
I
I would always try and recreate something that already has been shown to work, and see if you can add to the understanding what was going on in that process.
Yeah, that's the ideal scientific method. My approach was, let's uh, put in a blender all this knowledge
Well, I mean,
uh,
like I
and
said,
come
you
up with
combine.
something very simple, just as a sanity check, and look what came out.
Yeah. Oh no, I'm not saying do it exactly the same, but like, if you want to create electricity, there's ways that have been shown to do that. If you want to create heat, there's ways to be
Mhm. Yeah, I'm going to
shown to
try.
do that.
I have on plan to introduce carbon, oxygen, hydrogen
Mhm.
uh, household
The
items.
thing is,
Maybe potassium carbonate would
okay,
be
so
one of the dust that I would like to zap, see what happens. You said also boron. Maybe I smash up some boron glass and introduce it, zap it.
okay,
See
just
this simple half-hour stuff.
pause.
Okay.
These materials that stop the structures, if you have them inside the mix, then they prevent the clustering. They actually they capture them before they're able to group together. So you need them as a secondary material. Are you with me? So
Yes.
the carbon the carbon if you go and look at what I shared about uh what's his name? Anatoly Klimov. I mean, I worked it out that neutron capture materials seem to capture whatever it is that's doing the work in Lena. Um, and then that kind of forced Anatoly Klimov in 2018 to privately admit to me, and then it took me several years to get him to make it public, that he could only go over a COPF2 if he added a carbon a neutron capture material like cobalt or indium or gadolinium or boron. Okay. Of course, lithium does as well, lithium six predominantly, but then you get fission and stuff. Um, but of course, carbon is a very good moderator, and it moderates. Thing that's doing moderating is actually capturing thermal energy
Capturing.
from it. And so I've discussed this because if you add any hydrocarbon to a Mars gas or even an ordinary Brown's gas, it takes it from doing the Lena and coherent matter magic into
To
a
doing nothing.
it just does more thermal stuff.
Mhm.
So
Oh,
what I'm trying to say is you do want to not lose your strange radiation, your coherent clusters, but you want them to do the magic first, which will compound the amount of these clusters that you produce, and then you capture the bulk of them in the secondary material, which is your thermalizer.
yeah, but in my view, it's not counterproductive. I mean, the fast transient plasma discharge
Mhm.
is to create these
Mhm.
plasmoids.
Mhm.
Then the surrounding material can be used to feed it,
Mhm.
and interaction between these well-fed individuals and the collapse afterwards and the capturing of whatever comes out as neutrinos or radiation
Clusters or something, yes.
with the same material that's in the mix, that's that heterogeneous material mix. Then it's also a fuel, it's also a capture material, also a heat transfer material. So That's the way I'm thinking about it. But
Well, I mean, you're more in line with the Suhas Ralkar fuel producer, where he couldn't get cheaply in India 5 micron sized powders of the things that he wanted to test in his LENR reactor, his plasma discharge reactor. So he used his expertise to try and ultrasonically mill materials, and this produced this material that was ridiculously active. And this was the first strange radiation that I saw, and it shredded
the plastic
polycarbonate.
container, yeah.
Yeah. And did you see the video that I shared on Sunday with the cold fusion star and the neutrino detector?
Not entirely.
Okay, so basically they had this 27 megawatt producer of 70 giga electron volt protons every 7 seconds of 10 to the however many was protons at this energy, and they would go through 100 and whatever it was 40 meters or something of vacuum tube to cause the spallation products to decay, them using pions and kaons to decay. And then they went through something like, I don't know, 49 meters of iron in order to remove everything else, so that the only thing that could possibly get through, not even bosons and not muons or whatever, the only thing that could get through would be a neutrino. And they show that a neutrino it collides with the freon, one of the atoms in the freon, and causes this energetic event with these various subatomic particles coming out. And one of them is a muon, and the muon goes away and causes an interaction that produces a star which looks literally exactly like the what Matsumoto calls cold fusion stars from his 1 point cold fusion experiments. I mean, it looks identical. I mean,
Okay.
totally identical. So the conclusion is there. I mean, it looks exactly like that,
Yes.
right? And this is what we saw coming out of the ultrasonic fuel. Now, when I analyzed the ultrasonic fuel by Suhas Ralkar, he said, "Where's the tungsten?" I said, "Well, I didn't see any tungsten in there." He says, "Well, I used tungsten as the hard element to smash everything up." And at that time, I hadn't had all of these different data sets, and I hadn't realized about Mizuno in the 1990s with his tungsten wire. And we hadn't seen at that time the tungsten disappearing in the Vega experiments. Basically, the tungsten fissions like spectacularly into other elements. And that must have created a huge amount of heat. But that 4.5 kilowatts of sound is also 4.5 kilowatts of sound. So he had to build in a very good cooling
Cooling
system.
system. Yep.
So he had his ultrasound chamber and then a chamber around that where he was fast flowing through a very large volume of cold water.
Yep. I'm guessing he did not look at the
No,
energy balance of the
no,
system, because this
no.
was just to make the powder,
Yeah. And he had
which
carbon in
goes
there.
in another.
He had potassium carbonate in there. He had titanium. He had the various things in there. You can go and look at the old Steemit blogs and you can see that. So that is kind of what you're talking about. And I imagine that would have produced fantastic amounts of heat. Certainly, we got lots of heat when we were doing the ultrasound with the aluminium, but aluminium, when it gets deoxidized and produces a reaction with water, that produces heat. So we weren't doing a heat balance on that. I was just looking for definite production of hydrogen, which means, from my point of view, when you've got the aluminium oxide being removed in the coherent ultrasound structures, you have these vortical things that like to feed on things with a magnetic moment. And what you do is you get atomic hydrogen produced exactly where it needs to feed the structure.
Yep.
It's like fed in like pipette exactly where it needs to go. It's made and then it's eaten. So it's a self-feeding process, and that kind of same thing would have been going on likely in the system of Suhas Ralkar. So you're looking effectively to create these clusters that are able to do this matter disassembly and then break them up at a point where you're trying to get the energy gain out of it without and you're looking at lots of small localized events to create your outcomes, yes?
Yes, exactly. A small duration, limited fuel, small setup, um, which I can feed in very precise amounts of electrical energy. It can be very precisely measured, but in order of watts. Watts going in, and the entire. Imagine taking a glass vial. You insert two electrodes, and on the bottom of the vial, where the electrodes end, you put a half a teaspoon of powder. You seal it up, you hit it with, I don't know, 1 minute of pulses with 5 watts average going in, and the entire thing during this duration is inside a calorimeter.
Mm-hmm.
And you can put also your capacitors in the calorimeter, because that's after the capacitors where you have the high amplitude current, there you have the losses. I squared R losses are dominant in there because I is kiloamps, I squared is very large number. So the capacitor and the wires after the capacitor heats up together with the vial. You put that in a calorimeter, you can get the heat out, and you look at the energy going in. It's a very simple setup, and you can test a variety of elements in
Okay,
a
I know what
brushed
you're
up,
talking. I know what you're
dusty
talking. I
form.
know what you're talking about. So, um, might I have a suggestion then for the thing to test?
Yes, that's what I was trying to get out of you in the last 15
Yeah,
minutes.
well, now I understand what you don't want to do. It's that's helpful. Um,
Uh,
I,
well,
I just not
I'm
adding.
I'm a hobby experimentalist, and I have limited time on
I
this.
understand. I
I'm
understand.
very enthusiastic about it, but I'm not a big budget researcher trying to break down the fundamental physics of it. I'm
Well,
just
you're
throwing things together and hitting the lucky button.
you're definitely in the right company then. Because we ain't big budget either, never have been. I think we've probably spent CERN's stationary budget for one day in our entire existence. So yeah. However, if you go and look at Kladoff's work on remoteview.icu, and you look at what his reactor that produced the most excess heat. What he did was he added aluminosilicate. And this is right in line with the experiment you've already done because you had aluminium in there and you saw silicon coming out.
Mhm.
And when he added aluminosilicate, he produced the most excess heat he did in any of his cavitation experiments. And we are saying that cavitation is the same process as is going on in ball lightning. And therefore, I would suspect this would be your fastest route. So, for instance, if you fuse two aluminium 27s to iron 54, you get 21.8426 mega electron volts for one reaction.
Yes, that's what we want to target, the mega electron volt range.
Yes.
But
If you use
uh,
aluminium with silicon 30, so aluminium 27 with silicon 30, you get iron 56. So all of these reactions don't go beyond iron 57. Aluminium 27 plus silicon 30, that gives you iron 57, right? So in every case, the weakest reaction here involving aluminium and silicon comes in what is it? Uh, it's an exchange reaction where you get aluminium and silicon 29 gives you deuterium and iron 54 and 4 million electron volts. So it's already a million times more energy per reaction than roughly the most energy you can get from a chemical reaction of the order for the weakest reaction. And the most common one are aluminium 27 to aluminium 27. Iron 54 is the most energetic at 21.84. So that's on Ultra method for obtaining energy. And I break down the equations for what he did in his patent. And where are we? I will look at. So that's that paper. Method for obtaining energy. Yeah. Oh, that's just the link to the main patent. Yeah, just search on under Kladoff. There's method for obtaining energy, and the other one. There's only really two that you need to look at there. The patent, I do a read through, and he has down the bottom where he adds the table. I should have put that in. Actually, I think I need to actually manually reconstruct that table.
But this was a cavitation system, right?
No, but it's the same process. It's the same process.
No, but I'm thinking what else could be involved? So there's water involved.
So look, if you look at examples 2 to 12, his example 13 was a 5% aluminosilicate suspension. So you just get your aluminosilicate, and that produced a COP of 11.61, by far the highest, and it's one of the highest ever recorded in Lena.
Yeah, I recall seeing that paper, but this would not be a dusty fusion.
Well, how long do you?
Or do I need water? Do I need a?
This is water. It's a suspension in water. Yes.
Yes, that's what I'm trying to find out. If oxygen is in there in the
water,
aluminosilicate. No, in the silicate.
It's also in the aluminosilicate. You could try it dry. Yeah.
Yes, but hydrogen not. Hydrogen it might be in the water.
It will be in the water.
So water might be important, and hydrogen might be important.
Hydrogen is 2,000 to 4,000 times easier to produce this magic stuff that comes out of it.
Yes, that's why I'm thinking to try maybe a dusty plasma discharge.
I don't think
with hydrogen gas.
You could try it in hydrogen gas, yes.
Yes, that might be a very potent fuel mixture.
If you're going to do this aluminosilicate, and you're going to have that in hydrogen gas, I would make sure you are a long way away from it when you trigger it.
Yes, I was also wanting to follow up on the strange radiation and shielding methods. You mentioned.
Hold on. No, I don't mean just strange radiation. I mean sheer explosive capacity. So, did you see the first part and the conclusion part, because I don't think you saw Sunday's presentation, but anyway, Klimov talks about the reason that the West is pursuing hydrogen metal energy is for new explosives, new propellants for rockets and torpedoes, and he cites the the Alice propellant that was tested.
Yeah, ice with aluminum nanoparticles.
Yes. And do you think aluminosilicate with EVOs is not going to be doing exactly the same thing?
Yep.
I'm saying this could be, and he says this is like up to 100 times more explosive than TNT.
Yes.
And
if you're looking for heat, then be prepared also for the worst far end of heat.
This is what I'm saying. what I've just showed you is we know from your current experiments that aluminium and water leads to these iron crenellated spheres and silicon. Okay. We know that the most energetic experiment by far, and I've done all the calculations as to why in my blog, is just a 5% aluminosilicate suspension. Okay. I've told you that the nuclear remediation in the 1980s of Yul Brown used whatever it was with HHO and aluminium and iron. Okay. So you have aluminium, water, aluminium, water. In your experiment, aluminium, water in this experiment by Kladoff, and aluminium and water in the experiment that's able to do nuclear reorganization in the 1980s. It's the same thing in each case. And you have this Alice propellant. And I've also told you that 49% approximately of the mass of Castle Bravo was aluminium. And that Avi Loeb recovered within the fallout zone iron-rich crenellated microspheres, which contained uranium and two other elements used in thermonuclear bomb. Okay, and I think the iron-rich crenellated spheres in there are produced from the aluminium housing of the Castle Bravo bomb. I think aluminium is the key here. Aluminium is the most affected element by far by the Hutchison effect, and aluminium is a single isotope. It's paramagnetic. It's the fourth most conductive element. It has like the other three most conductive elements. You know what they are? Gold, silver, and copper, and all of those are diamagnetic. You know what the next most conductive element is? Tungsten. What have I said about tungsten?
Tungsten can sublimate.
Tungsten does these massively energetic events, like in the
HHO.
With those kind of systems, and it disappears.
Wait, it boggles my mind. Why didn't anybody try to check the power balance or energy balance of a HHO flame on top of a tungsten, maybe on top of water?
Go and look at my blog. Go and look at my blog. The highest energy excess ever achieved by Mizuno was when his tungsten electrode vaporized, and it had a COP they calculated of 800. That's in a water electrolysis. He raises it to about 70 degrees, just like is done by Binger and Huang. The reason being is that you need to get it to the point where it starts to phase changes rapidly, and that leads to these processes occurring, the cavitation occurring, right?
Yeah,
you have this.
This is a very simple experiment, right? An HHO producing cell and a piece of tungsten and a bath of water and a thermometer.
Yes, it is.
This is also pretty basic. Like, yes. Also you can buy plasma cutters, right? You feed in water and argon gas, and it just shreds all types of metals. Why don't you buy a plasma cutter, monitor the energy from the wall with a wattmeter?
I'll tell you why people don't do it. It's because, one, they've got limited time, and two, 99.99999% have been programmed to think that this isn't possible. So they already know they're wasting their time. Look at your own experience.
It's obvious. If that plasma cutter, it just shreds metal and it boils metal, and it seems to be more energy efficient than any angle grinder trying to munch its way through a sheet metal. Then you just need to buy the damn thing and check the energy balance and see.
Believe me, for 3 years I've walked past the plasma cutter specials in Lidl every year, thinking I've wanted to do that experiment.
Me too. Me too. But
But I haven't had the money
I
in my
did
pocket
agree.
to do it. So here's the thing. We know aluminium is the key to these energetic processes. Look, what is the most effective material that Tesla was able to produce his dark matter rays with? Aluminium. What is the most what is a very effective material proven that produces exactly the magnetohydrodynamic structure in recent days? That is an aluminium electrode in Griffin Brock's desmetron tube. It's aluminium. You can try and find another universe where there's a better thing to do, but it's aluminium. And there's plenty of it. It's ridiculously abundant element. So like it's already going to be way more than anyone needs. So we probably should focus on it.
Yes, I think this crowdsource based investigation needs to ramp up with these simple experiments with many equipment that people already have. They just need the information. They just need
They
a
just need the information.
catalysis.
That is the whole
Yeah.
point. That's the whole point. See, for me, I had to go through the complex baptism of fire of replicating Chelani's work, which involved a very serious investment by an interested party at the start. When we saw the excess heat, which was on our second attempt, the project was only a couple of months old in December of 2012. I was hooked. And unfortunately, you're probably suffering the same thing now because you don't believe it up until you've done it yourself. And then you've done it yourself and go, oh shit, now it's real. And what I'm saying to you is I'm shortcutting the process for you. I've done the hard work. Aluminium is what is the key. And carbon also, depending on, which way you want to go with this, light elements that can fuse easily to give you massive net gains. And
Mhm.
aluminium has this unique property of being both paramagnetic, cheap, light, single isotope, so it can become bosonic very, very easily, and highly conductive. It's just
Aluminum
perfect.
is special on the periodic table. I was opening up a periodic table and going from the lowest uh, atomic mass to up until iron and seeing, okay, which form of these uh, elements and molecules of it and stable molecules of it and non-toxic molecules of it would I be able to access easily in a aqueous based solution or a powder form. And I was writing my list. Okay, let's try these stuff consecutively in a test vial between two electrodes and a plasma discharge and see what happens. To see what happens in terms of sieving it to a magnet to see if ferromagnetic spheres would be produced, and the calorimetric approach. And by the way, on my early posts on the forum on copper electrodes, I also have a strange small little translucent sphere, which I don't have access to EDS. I don't know what
It's
is
it's
that made
it's
of.
okay. Copper does the same thing. Copper's interesting because it's diamagnetic and it does not absorb hydrogen. So you get hydrogen bunching when it's a cathode because all the protons try to get near the cathode, but they can't go into the cathode, so they cause a bunching. And you know where that's exactly explicitly said? In this book.
Yep, it's in our face, but we need to actually stand up from our PC and from our phone and lift a finger and do something.
Yes. And you're doing it, and that's good. But you don't have to fight the battles. The battle's already been won. It's aluminium.
Okay.
I said it in 2017 in India. I said blah 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 blah. Aluminium has these unique properties. You can't make anything else unique. Aluminium's got it all. Yes, you've nearly got the same conductivity with tungsten, but it's really expensive and hard and so on. And it does fissioning and it fissions to lots of things. whereas aluminium tends to fuse because it's that end of the spectrum.
Yep. Everything goes to lead.
Well, firstly, it goes to silicon. Well, everything, no, well, a lot of it, things try to go to iron, but it depends how much energy. If you keep forcing energy in, like um, with Kladoff, I mean, and even with with Kladoff, after a certain number of hours of running his device, he was getting every element in the periodic table. The longer you ran it, the more elements you got. So it's yin yang. So some will be resonantly producing heavier elements, and some will be tearing things apart to feed the thing that wants to make heavier stuff. In the case of SV Adamenko, he was creating things of 455 AMU. These don't exist in our near universe, right?
Yeah.
The,
Maybe you don't want to run in experiments very
no,
long.
I mean,
Who knows what you end up with?
Leclerc nearly killed him and his colleague in just running his aluminium perforated Swiss roll in a pressure drop with a standard pump from a garden, pond, and he
Yes.
produced all the elements in the periodic table with aluminium and water. Do I need to be any more obvious?
Yep, it's quite clear.
And you're
Yeah, but
already doing it.
one needs to be aware of the risks, and the best practices need to be applied for shielding. A distance need to be kept. Unfortunately, I'm not aware of devices and details on devices that are able to detect strange radiation.
So you need to go to my Steemit blogs, and I developed a system where I got the guy who produced the Cosmic Ray Finder to produce a better version of it, which you can download from the link. And essentially, you take an old 920C Logitech camera. They're not cheap, but they are good. And you cover it with PTFE tape. I did that because it's the only thing I had to cover it at the time. But it turns out that excites the clusters as they go through, because it was a fluoropolymer that usually Bajatov used to excite the clusters coming from his water meniscus discharges, so that he could detect them in his Geiger counter. It was an accident for me, but it turns out that that's exactly what you need to do, you can see, but it was in many weeks of the observing Suhas Ralkar's fuel that I found a few non sort of muon, non sort of beta particle traces. And they had exactly the right shape for a strange radiation trace, and the right scale.
So you can imagine a scintillator type device with a PTFE film, and okay, that produces visible light. How does it excite
I think
the PCB?
the best approach is the way that Matsumoto did it. Matsumoto took radiographic film and he produced a stacked array, right? And the reason you do a stacked array is because in my sensor, the CCD, if it goes through and it just goes through and it doesn't go along, it just makes a point and you don't know what you've got.
Yeah,
Whereas if you have a stacked array,
it's like a noise on a pixel.
yeah, with a stacked array, it can go through and then it gets to a point and then it travels along, then it'll produce the right track. And so what you do is, I think the right approach is to get those. You can buy them from India. They come pretty quickly. And you buy a box of 50 and you put a stack of 20 in a suitable
Yeah,
place.
I've looked into them, but that's not a real-time monitor, right? You
No,
need
but it's
to
good
build
because it
them, develop
accumulates.
them.
No, but it accumulates over time. So what you can do, the real-time monitor is what I've described in the first description, using a CCD, using a webcam. And it shows you the time event, it shows you the image, and you can see it.
But I'm looking into something electronic like a scintillator. with a real-time output, because the problem with these films is, in my opinion, that by the time you develop them and conclude that, oh my God, you had been exposed, it's too late.
Yeah, oh, okay. Mm.
It, I would much better prefer a real-time system which tells me immediately, or even an automated real-time system
Well,
which
I
detects
would get
a
one of
level and shuts
these
down
little
the input.
scintillators. They're a few €100, and they've got a little scintillation detector in there, and you could put some silver foil or PTFE around that to activate them.
That's interesting. I have Geiger Miller tubes, but I'm not sure that's the perfect device.
No,
I would much prefer something with a much larger cross section,
yeah.
so it can capture a wide angle and give me real time output. I'll look into this device, which I know it can detect X-rays and various nuclear radiation.
Okay, great. Just be aware that Evos can mess up any electronics whatsoever, which is why I prefer solid state detection if possible. When I mean solid state, I mean really solid state, like film. And the good thing
like
about film is
like
that,
disposable film. Yeah.
yeah, even just normal 400 ASA film, just the rolls, you just put them around your experiment. You're going to have to know that if you are producing iron-rich crenellated spheres, you're going to be producing EVOs, and a proportion of them are going to be coming away. We've got a situation right now where the extremely expensive vacuum gauge in Hinck's experiment is dead. And when they looked at it under the SEM, you can see the EVO marks. And this was all the way down a long tube and so on. So we're debating whether to spend €195 to have it sent back from Liechtenstein so that I can take it apart and actually look on the actual sensor head. Because we're at the moment, we're just looking at the plasma shield, and you can see literally the impact marks of the EVOs.
Yes, but you know that EVOS likes voids crevices, so it will happily
Yeah, I
travel
know,
down
but you had to
a
go all
small
the way
pipe.
down a long tube because it's
No problem, it likes it.
yeah. So we're going to have to pack the tube with iron wool or something.
Well, uh, iron wall. Luciator mentioned thick iron wall, but you've mentioned thin aluminum construction with a plastic film, so a multi-layer
Well, yeah,
structure with.
that's no, but you've got to allow the gas through. I'm talking about the thing needs to be gas molecule connected to the chamber because it's reading the vacuum, right?
Yeah, but if you look at the Evo as it has an electrical
No, it might be neutral.
wavelength or something, so it can interact with a thin aluminum metal more with a thick one. So you can fill the tube with some alumina-based powder, and
Yes,
hopefully
yes,
that will stop in its track. But
yeah,
it will let the gas through, of course.
yes. Anyway, we're thinking along something along those lines, right? It's
Okay.
half past midnight here, and I have to get my beauty sleep.
Okay, let's close up shop. Well, for me, it's it's a unique opportunity to speak directly to you. Well, I was months ago. I was uh, trying to figure out how to actually contact you by mail or something in chat, whatever form, just to share with you some, for example, the Nesterovich paper.
Yes.
I was wanting to push that through somehow so you could see it, because I did not see that one featured on your blog. So I'm
I
very grateful for this call.
Yeah, it's a pleasure. This is what happens when you prove that you're actually going to bother to do something. Things will find you, and that's what's happened when like people have either there's a lot of people that that would pass criticism. There's a lot of people that will tell you what to do, but there's only few people that will actually take the initiative to do something themselves. And what you've shown is you've gone through a step procedure to try and at least get to a point of acceptance for yourself that there might be something going on here. And you took the bait with doing the SEM with an experiment that you were happy enough to say, I'm not contaminating this, at least not obviously. And you produced exactly the same things that we produced in a carbon Eagly dusty fusion. I remember it was just outside well, it was about an hour outside of uh, Budapest in 2016. It was a hot, sunny day, and we were doing it outside. And you can go and see all the videos. It's on the channel, and you can see the videos of the analysis. And I've shared those images many, many times. But it wasn't until later data came in that I started to notice the crenellations and the magnetic alignments. And I'd already noticed that for some reason it was picking up the silicon dioxide as well as the aluminium. And I'm thinking, why is the silicon dioxide being picked up with the magnetic particles? You know what I mean? Something interesting is going on there, and it's like, right. And I'm thinking, well, is it actually an iron sphere that's covered with silicon dioxide? And later on in the work of my colleague Alan Goldwater, when he did, I said, go, just get some aluminium and you've got the cavitation device, just run it for as long as you feel comfortable, and then run a magnet around and see if you can find some iron crenellated spheres. And the next email he sent me, go, oh, found these.
Yeah, I need to thank you for those videos, for those conference presentations to being shared. I think that is a very good catalyst for all the people out there.
Yeah, well, they've been well received. They've been well received, but again, I come down to it. Few people actually act on it, and I mean, when people, I just feel sorry for people more broadly in the field that have chosen to actively ignore that work. Because it was a collective effort. You know, I put the idea out at ICCF 22 in 2019, and it was 7 months before Alan Cuss came back, because I said, just find some metal and run the experiment with it, and I think you're going to see something interesting. And Alan Cuss did it because he had aluminium kitchen foil at home, and so the rest is history. But and you know, of course, Binjun Huang did it with copper foil, same thing going on, and you know, we are where we are. But aluminium really is a magic element in this, and it's so abundant. It's hilarious. It's just hilarious. Yeah. All right, Tibi. Okay. Have a great evening. Thank you for taking the call. And
thank you. The same to you. Have a nice evening. Get some good rest, and I hope we'll talk again and do some variations of this experiment.
I think we will. Yeah, aluminosilicate. It's just moist and stand back.
Okay, noted.
A big distance, not just because of strange radiation. I'm saying because of bang.
Okay, small dose, take it easy. Noted as well. Okay, thanks for the talk. Thanks for the information. Have a good night. Bye-bye.